The topic of our experiment is speed control of DC shunt motor by armature control. The aim of this experiment is to control the speed of a DC shunt motor using the armature control method. Moving on to the apparatus required for this experiment. Number 1 is the power supply, which has a current range of 0 to 8 ampere and voltage range of 0 to 240 volt. Number 2 is the ammeter. In this practical, we use two ammeters. The first one is to measure the field current with a range of 0 to 2.5 ampere, and second one is to measure the armature current with a range of 0 to 500 milliampere. Number 3 is the voltmeter with a range of 0 to 250 volt, which is used to give the power voltage supply. Number 4 is the DC motor, whose speed we will be measuring. It has a field current of 0.7 ampere, field voltage of 180 volts, armature current of 2.7 ampere and armature voltage of 200 volt. Number 5 is the tachometer. This device is used to measure the speed in RPM. Number 6 is the rheostat with the specification of 1150 ohms with 0.6 ampere current value. Finally, we have the connecting wires, without which no experiment is possible. Now for the theory part of armature control method. In this experiment, we will be controlling the speed of a shunt motor by using the armature control method. The armature control method requires a change in the voltage applied at the armature terminal without altering the field current, because change in field current will change the common voltage supply impressed on both the armature and field, which will affect the speed of the motor unless the voltage change is huge, whereby the general working of the motor will be unstable. This is the circuit diagram of the DC shunt motor. When the power is on, then the voltage supply will be given and the current will flow in this direction from the positive terminal. The field and the armature terminals are in shunt, so the voltage across these two terminals will be the same. Now, if we connect a variable resistance at this point in series with the armature terminal, like this, if we connect a variable resistance here, this is in series with the armature terminal, then the resistance will oppose the flow of current, thus decreasing the voltage across the armature terminal and so decreasing the speed of the motor. The introduction of this resistance will make the voltage and the current across the armature terminal to drop, and the speed will also reduce because the voltage is being dropped. This is because voltage and speed is directly proportional to each other. This is the relation between the variable resistance, the voltage and the speed of the motor. So if the variable resistance is increased or is given at the maximum, then the voltage will be decreased, and since the voltage is decreased, the speed of the motor will also decrease. The speed of the DC shunt motor is given by N is equal to K times V minus IARA whole divided by phi, where speed N is measured in terms of RPM, V is the applied voltage in volts, IA is the armature current in ampere, R is the armature resistance in ohm, phi is the field flux in Weber per pole, and K is the constant for a given motor. This K can be calculated by multiplying Z and P, which is divided by 60 times A, where Z is equal to number of armature conductors, P is the number of poles of the motor, A is the number of parallel paths in armature circuit. From the relation above, the speed of the DC shunt motor can be varied by varying the voltage V applied to the armature, where voltage the armature, when the armature voltage is decreased, then the speed of a DC shunt will also decrease, and if it is increased, the speed of the DC shunt will also increase. Number 2 is the armature circuit resistance RA. If the resistance RA is increased, then automatically the V will be decreased, and so the speed of the DC shunt motor will also be decreased, thereby affecting the speed of the DC shunt motor. Number 3 is the flux phi. The speed is nearly proportional to armature voltage if the armature drop is small, while it is inversely proportional to the flux phi. The speed variation is plotted against armature voltage or field.
Procedure of a speed control of a motor by varying armature voltage with field current kept constant. Procedure number 1. Connect the circuit as part the circuit diagram. In this circuit diagram, we have shunted the field winding with an armature winding where E1 and E2 are the terminal of a field and A1 and A2 are the terminal of an armature. Procedure number 2. Connect the rheostat R1 in series with armature winding with minimum value. Procedure number 3. Give the power supply Vs and note down the rated shunt current ISH and also the supply voltage. Now connect the voltmeter in parallel with the DC supply and also connect the ammeter 1 in series with E2 to measure the field current, and also connect ammeter 2 in series with A1 to measure the armature current. Step number 4. Increase the value of R1 and note down the armature current IA corresponding to the speed in RPM. Step number 5. Plot the graph between speed and armature current.
Some of the precautions we should keep in mind during the experiment to obtain accurate results are making sure all the connections are tight, verifying the circuit before giving the power supply, not touching the live or naked wire when power supply is given, increasing the resistance carefully, using the instruments with proper readings, and measuring the speed using tachometer properly. The last precautions, that is, wearing shoes when working in the lab, is for our own safety, and handling the instrument with extra care is because the instruments are very limited and very expensive.
In this experiment, speed control of DC shunt motor using armature control method, we are going to use a source power supply. From the source positive terminal, we will connect it to the E1, that is the field terminal, and from the same terminal, we will connect it to the rheostat, that is a variable resistance, and from another terminal of a rheostat, we will be connecting it to the negative terminal of a ammeter, which is to read the armature current, and from the positive terminal of armature to measure the current, we will connect it to the terminal of a armature, and from the another terminal of a armature, we will connect it to the ammeter positive terminal in order to measure the field current, and from the negative terminal, we connecting it to the E2, the terminal of a field. And from the E2, we will be connecting it to the negative terminal of a source, and we are again connecting this voltmeter in order to measure the voltage of a supply. Now we will give the power supply. Gradually we will increase the source supply. We will be giving the supply up to 200 volt, which is rated voltage of a DC motor. Then we will measure the field current of the DC motor, which is 0.3 ampere, and also we will measure the speed of a motor in RPM. Here we have 1529 RPM, and the armature current reading gives 110 milliampere. Now we will increase the resistance of rheostat, and our assumption is that when we increase the resistance of rheostat, the speed of the motor will decrease. So let's see. Our armature current is dropped to 100 milliampere. Now we will measure the speed of the motor, which is 1340 RPM. So our assumption was right.
For the observation table, these are the values we obtained after doing the experiment. Moving on to the graph, we observe that the speed decreases as the current is decreased. For the results, the variation in speed of shunt motor with respect to armature current is shown in the observation table and plotted on the graph, that is armature current versus speed as shown earlier. And from the graph, we observe that as the armature current in milliampere is decreased, the speed of the DC shunt motor also decreases linearly. Now for the discussion, when doing this experiment, we had to change or increase the variable resistance very carefully so that we could see the changes in the armature current and the speed in the DC shunt motor. Thus, we observed that our assumptions that we have already stated when doing the connections were correct. Finally, we conclude that as the variable resistance is increased, the voltage across the armature terminal is decreased, and so the armature current and the speed of the DC shunt motor also decreases, and vice versa. Thus, resistance is inversely proportional to that of the voltage, which is directly proportional to the current and the speed of the DC shunt motor.